to the machine design series. Today we are covering an example that involves the fatigue of helical compression springs. In previous videos, we've covered conceptual, theoretical, and the equations that involve equations for the analysis of helical springs in fatigue. And today we're going to put it together using an example. And so give me a minute, I'll write out the problem statement and then we'll get into it. Okay, so this is a bit of a wall of text, but we're going to break it down so that it makes sense, and we're going to fly through this problem. All right, so this is example 10-4 in your textbook, so let me just write that over here in case you want to follow along. Although there are some minor mistakes in the textbook, at least in the version that I have, and so as we go through this problem, we're going to correct those mistakes. I'll try to point them out when I can. So with that, let's get into this problem. We have an as-wound helical compression spring that is made of music wire. It has a wire size of 2.33 millimeters, an outside diameter of 14.28 millimeters, a free length of 111.28 millimeters, 21 active coils, and both ends squared and ground. The spring is unpeened. The spring is assembled with a preload of 22.24 newtons and will operate with a maximum load of 155.68 newtons during use. And the first part of this problem asks us to estimate the factor of safety guarding against fatigue failure using a torsional Gerber fatigue failure criterion with Zimmerli data. Okay, so that's a lot to take in all at once, but let's break this down piece by piece. So starting with our problem statement, I'm just going to pull out the parameters that are given to us. So we know that we have a wire size of 2.33 millimeters. I think that's the first value we can write down. So we denote that with the lowercase d. Next, we have an outside diameter that's given of 14.28 millimeters. So that's capital D sub O, 14.28 millimeters. Remember, that's not the mean coil diameter, which is capital D. It's the outer diameter. We're going to have to calculate that mean coil diameter. We have a free length, which is capital L sub O, of 111.28 millimeters, 21 active coils, and that's denoted with a capital N sub A. It's 21. And both ends are squared and ground. We will keep that in the back of our mind to use a little bit later with a table. The spring is unpeened, and so we know that we're going to need to use the Zimmerli data because that's asked of us in the first part of this problem. And we're told that the spring is unpeened, so that tells us exactly which Zimmerli data that we need to use. We need the Zimmerli data for an unpeened spring, and that is capital S sub SA equal to 241 megapascals, and capital S sub SM is 379 megapascals. And next we are given a preload of 22.4 newtons. So I'm going to denote that as F sub I for an initial force, 22.24 newtons. And we'll operate with a maximum load of 155.68, so that's going to be my F max. Okay, and then the problem asks us to estimate the factor of safety using a Gerber fatigue failure criterion. So we haven't seen the Gerber fatigue failure criterion much in class, but it is useful for a demonstration in this problem. So let's write out what the Gerber failure criterion actually is. It is our alternating stress over the endurance limit plus our mean stress over the ultimate tensile strength squared equals 1. It looks really similar to the Goodman failure criterion, which we have used a lot, except for this second term obviously is squared. And also in your textbook, you'll find a formula that solves for the factor of safety using this Gerber fatigue failure criterion. It's not as straightforward as just inverting this ratio as we do with the Goodman failure criterion. So we need an equation. If this was a problem on an exam, I would give this to you. So our factor of safety is 1/2 of our ultimate tensile strength over the mean stress squared times the alternating stress over the endurance limit, all of that times -1 plus the square root of 1 plus 2 times the mean stress times the endurance limit over the ultimate tensile strength times the alternating stress. That ratio is squared. All of that goes inside the square root and we close parentheses. Just barely got that to fit. Okay, bit of a long equation, but we know what all of these variables mean, so it's just going to be a plug and chug in the end. And next, we see that it says we need a torsional Gerber fatigue failure criterion. So the form that we have this in here is for normal tensile stresses, and we need it for torsional shear stresses. So I'm going to rewrite this equation, replacing my normal stress components with shear stress components. So I have 1/2 of my torsional ultimate strength, or the torsional modulus of rupture, divided by my mean shear stress squared times the alternating shear stress over the shear endurance limit times -1 plus the square root of 1 plus 2 times my mean shear stress times the shear endurance limit over torsional modulus of rupture times the alternating shear stress, that ratio squared, finish our square root, and close parentheses. Okay, so now let's go about finding each one of these parameters that we're going to need to plug in to this equation in the end. So first of all, I'm going to look for this torsional modulus of rupture. If you remember, we have an equation that relates the torsional modulus of rupture to the ultimate tensile strength. It's equal to about 67% of the ultimate tensile strength. So now we need to find this ultimate tensile strength. We talked about that in our video on spring materials, and we said that the ultimate tensile strength is dependent on material and wire size. So we came up with this equation, which relates the ultimate tensile strength to material parameters A and M, and the wire size, which is this lowercase d. So if I look up in table 10-4, I can find the values for A and M for music wire, and they are 2,211 megapascals times millimeters to the M power, where M is 0.145, divided by my wire size, which is 2.33 millimeters, and that is to the M power of 0.145. So we can plug that into our calculator and find our ultimate tensile strength, which when you do that, you should come up with about 1954.96 megapascals. Okay, and now we just take this number, we plug it in up in this equation above. So 67% of that comes to 1309.82. Okay, that's our torsional modulus of rupture, and that's in megapascals. All right, so we've got that to plug in. Now let's look for our mean and alternating stresses. To find mean and alternating stresses, you're going to need mean and alternating forces. So let's look for those. The alternating force is equal to our maximum force minus the minimum divided by 2. So F max we already have written up here. This is 155.68. And now we need our F minimum. So taking a look at what we're given, think about what might be the minimum force. Pause if you want to. Take a second and think about it. And then when you're ready, come back and I'll tell you it is this preload value, right? We have a compression spring that has been preloaded to 22.24 newtons. So our applied force will never be less than this initial preload. We're going to start at this preload, we go up to a maximum force, and then back down to the preload and repeat. Okay, so it's 22.24 newtons divided by 2. All right, and that comes out to 66.72 newtons. Now let's find our mean force, which is going to be a very similar calculation. It's just the average of our maximum and minimum forces. So 155.68 plus 22.24 divided by 2, and I got 88.96 newtons. Okay, now we can plug these into our formulas for the alternating and mean shear stresses. So these are the equations that contain the Bergstrasser factor, and we multiply that by 8 times the force times the mean coil diameter divided by pi times the wire diameter cubed. And let me just go ahead and rewrite that for our mean stress. It's KB times 8 FM capital D over pi lowercase d cubed. Okay, so KB is the one thing we don't already have yet, and the formula for that is 4 times C plus 2 over 4 times C minus 3. Remember that C is our spring index, and that is our mean coil diameter divided by the wire diameter. And our mean coil diameter is just our outer diameter, which is the one that we're given, minus a wire diameter. So we plug all this in, we get 11.95 millimeters for the mean coil diameter, and then divide that by 2.33 millimeters. So C is 5.11, and that's dimensionless. Okay, now plugging that in to find our Bergstrasser factor. 4 times 5.11 plus 2 divided by 4 times 5.11 minus 3 gives me 1.287. And a good gut check is to make sure that your Bergstrasser factor is somewhere between maybe 1 and 3. It is a stress concentration factor, so normally it will be somewhere between 1 and 2. Maybe it could get as high as 3. But in any case, make sure that your Bergstrasser factor makes sense. It's not some really small number or really big number. Okay, and now let's plug it all in. We've got everything we need. So our alternating stress is 1.287 times 8 times 66.72 newtons times 11.95 millimeters. Make sure you're plugging in the mean coil diameter there, not the outer diameter. Divided by pi times 2.33 millimeters cubed. Okay, so that number comes out to 204.69. And we can use a little trick for our units. We know that one of these millimeters on the bottom is going to cancel, so we're going to end up with newtons per millimeter squared, right? Because one of these cancels with the one on top. And newtons per millimeter squared is the same thing as a megapascal. And you can take a second and go prove that to yourself. I encourage you to do that. You'll see that those are equivalent units. Okay, now the mean stress, 1.287 times 8 times 88.96 newtons times the mean coil diameter, 11.95, divided by pi times 2.33 millimeters cubed. And that comes out to 272.92, and again, that'll be megapascals. Okay, so now I have my mean and alternating shear stresses. I got my torsional modulus to rupture. The only parameter that we have left in this equation for our safety factor that we don't know is this shear endurance limit. And we're going to need to find that using our Zimmerli data, but it's going to be a little bit different from the way that we found our shear endurance limit with the Goodman criteria, because this time we're using the Gerber criteria. So let's write out what the Gerber criteria is in shear. It is our alternating shear stress divided by the shear endurance limit plus the mean shear stress over torsional modulus of rupture squared equals 1. Now if I replace my alternating and mean shear stresses with the Zimmerli data. So I've got S sub SA over S sub SE plus S sub SM over S sub SU squared. Okay, so all I've done is replace my alternating shear stress with the alternating shear stress data from Zimmerli. Same thing with the mean. So mean stress goes with mean stress, alternating stress goes with alternating stress. And then I can solve this for my endurance limit, shear endurance limit. And doing a little bit of rearranging, we find that this is equal to S sub SA over 1 minus S sub SM divided by S sub SU squared. Okay, so that's my equation to find my shear endurance limit. Now I just need to plug in my Zimmerli data and the torsional modulus of rupture, which I already found. So it's going to be 241 megapascals over 1 minus 379 megapascals over, what was my torsional modulus of rupture? 1309.82. Oh, and that's squared. That's one of the errors, I think, in your textbook when they solve for this endurance limit. Oh no, never mind. They do have the squared there. Okay. So calculating this, we get 263.40 megapascals. Okay, and with that, we are ready to plug everything in to this equation at the top and finally solve for our safety factor. Okay, so let's do it. It's equal to 1/2. Torsional modulus of rupture was 1309.82, and my mean shear stress is 272.92. Squared. Alternating shear stress was 204.69 divided by the endurance limit, which was 263.40 times -1 plus square root of 1 plus 2 times the mean shear stress, which was again 272.92 times the endurance limit, 263.40. All of that divided by 1309.82 times the alternating shear stress, which was 204.69. And notice that I have left off the units here. Normally I do keep track of units, but everything is in units of megapascals. They're all consistent, and they're all going to cancel, right? So I have megapascals on the top here, megapascals on the bottom here. Those cancel. Same thing here. These cancel. Over here, I've got 2 megapascal units on the top and 2 megapascal units on the bottom, so those will cancel. And that all makes sense because our safety factor should be unitless. Okay, so, but you'd have to have all of your stresses and strengths in units of megapascals for this to work. So they all have to be the same. Okay, and when you calculate this, I got I got 8.95 for this first part, and the second part in the brackets was 0.135. So finally, my safety factor is 1.21. Okay? So, this is my safety factor for infinite life using Goodman criteria, torsional Gerber failure criteria, with Zimmerli data. We're going to do the Goodman criteria a little bit later on in this problem. So, part A, this is the longest part of any other parts to this problem. So, if you're tired after that, don't worry, we are getting pretty close to being done with this problem. All right, so now part B tells us to repeat part A using the Sines torsional fatigue criterion, which ignores the steady stress component, and it asks us to use Zimmerli data for that. So again, this is something we haven't really talked about in class. If this were on an exam, I would give you this equation for the safety factor. It's pretty straightforward. We're just looking for the ratio of the alternating stress component from our Zimmerli data over the alternating stress, because we are ignoring the mean stress or steady stress component. So I can just go ahead and plug that in. I get 241 from the Zimmerli data divided by 204.69. That's the alternating stress that we calculated up here. And so that comes out to 1.18. Okay, so that is my safety factor using the Sines torsional fatigue criterion with Zimmerli data. And now we're asked to repeat again. So we're just going to rinse and repeat using a torsional Goodman failure criterion with the Zimmerli data again. So just move this up a little bit. So we know the Goodman failure criterion. I'm going to write it in the shear stress form, which is the alternating stress over the endurance limit in shear plus the mean stress over the ultimate shear strength, or the torsional modulus of rupture, inverted, all of that inverted. And we already have all of this from part A of the problem, so we can just plug this in. 204.69 over 263.40 plus 272.92 divided by 1309.82. Okay, and when I plug this into a calculator, I get 1.01. So really close to 1, probably far too close for comfort. So this is the safety factor for the Goodman fatigue criterion, and your book finds a different number. I'm not sure where they got their shear endurance limit from, so this is one of the errors in your textbook. They use a different number down here for this endurance limit, but we found that it's 263.40 in the previous parts of the problem, so we're reusing that again here. Okay, and then next we find in part D. This is a bit of a different question. We're going to have to do a little bit more work for this one. We need to estimate the critical frequency of the spring. So we need to remember that the equation for the natural frequency of the spring is 1/2 times K times G over W to the 1/2 power. And this is assuming flat plates on both ends. For an exam, I would tell you this, but if you're ever in a situation where you're not told and you think you need to make an assumption like this, so here we need to know whether it's sitting against a flat plate on both ends or just one with a free end on the other side, you can always do your work and just make sure it's clear what assumptions that you've made so that people can review your work and understand where you got your equations from. So to solve this equation, we need to find the spring rate, which is this lowercase k value, and we have an equation that lets us do that, or at least estimate it, using geometry and material properties. It is k equal to d to the 4th power times g, the shear modulus, divided by 8 times the mean coil diameter cubed times the number of active coils. The only part of this that we haven't already found is this shear modulus, which you can find in table 10-5 for music wire. And it is 81 gigapascals. So plugging everything in, we got 2.33 millimeters to the 4th power times our shear modulus of 81 gigapascals. I'm going to multiply this by 1,000 so that I can work in units of megapascals. Because again, megapascals and millimeters will cancel out to give newtons, units of newtons. So that it's just a convenient system to work in. And we're going to divide that by 8 times 11.95 millimeters cubed. And we have 21 active coils, as given in the problem statement. Okay, so calculating all of this, the number comes out to 8.42. And now let's think a little bit about these units. So they're going to cancel until we have left megapascals times millimeters, right? The millimeters cubed on the bottom cancels with 3 of the millimeters we have on the top. We're left with just 1. And then remember that we said megapascals is the same thing as a Newton per millimeter squared. We're multiplying that by a millimeter. So now we can cancel one of those millimeters that's on the bottom, and we're going to be left with units of newtons per millimeter. And we like to have spring rates, spring constants in this form because it's consistent with Hooke's law. So we have a unit of force on the numerator and a unit of distance on the denominator. Okay, now so for G, we know what G is. That's the gravitational constant. It is 9.81 meters per second squared. And W is an equation we derived in the video on critical frequencies of helical springs. It's pi squared times the wire diameter squared times mean coil diameter, not squared, times number of active coils times the specific weight of the spring material, all of that divided by 4. And this is music wire. Music wire is a type of steel, and so we're going to use the specific weight of steel, which we said in that same video, it's 76.5 kilonewtons per meter cubed, which is also equal to 76,500 newtons per meter cubed. And now I want it, so I'm doing all this work to get everything in newtons and millimeters. So now I can multiply this 7,6,500 by 10 to the negative 9 to get newtons per millimeter cubed. Okay, so this is just unit conversions to make sure that everything is in consistent units when we plug it in. So now I've got pi squared times 2.33 millimeters squared times the mean coil diameter, 11.95 millimeters, 21 active coils, and what is this, 0? Well, let me just write it how we have it. 76.5 times 10 to the negative 6 newtons per millimeter cubed. And all of this divided by 4. Okay, so you can see now why I converted these units to newtons per millimeter cubed. I've got millimeters here, 2 millimeters here, so all of this is going to cancel, and I'm going to be left with newtons, which of course is the correct unit for weight. So plugging this into a calculator, I get 0.2572 newtons. And this is slightly different from the value that they came up with in the textbook, rounds up to about the same. And then we are ready to plug into our equation for the natural frequency. So natural frequency is 1/2 times the spring rate of 8.42 newtons per millimeter times 9.81, and I'm going to multiply this by 1,000 so that I have, again, millimeters, units of millimeters for this calculation. If you wanted to, you could also convert everything to newtons and meters, and that works just as well. This is just maybe a little bit quicker because we have units that are closer to 1 when we use units of millimeters and megapascals. So anyway, our weight was 0.2572 newtons. Okay, and you can see, oh, and this is to the 1/2 power. So now my units are going to cancel. I'm going to have these newtons cancel with these newtons, these millimeters cancel with these millimeters, and I'm going to be left with 1/seconds squared. I'm taking the square root of that, so I'm going to be left with 1/seconds for the unit. And 1/seconds is the same thing as a hertz. So my natural frequency is 283 hertz. And if you remember from the previous video, the significance of this is that we want to make sure our forcing frequency is significantly far away from this natural frequency of our spring. And we said about 15 to 20 times. So if I take 283 divided by 20, I get about 14 hertz. So I want to make sure that my forcing frequency is going to be less than this 14 hertz. Otherwise, I'm going to start getting too close to the natural frequency of the spring. And to further help this make some physical sense, we can convert this to RPMs just by multiplying it by 60, and we come up with 840 RPM. So if this spring is in a system that is going to be rotating faster than 840 RPM, then we need to consider a redesign of this spring. All right, so that is the end of this example problem. I hope that this was helpful, and this also concludes our section on helical springs and on springs in general. In the next video, we will start talking about bearings. So thanks for watching, and I hope to see you in the next one.